The LSTM neural network. What is it used for, and how does it work? Welcome to our first machine learning video, Artificial Neural Networks, Recurrent Neural Networks, and LSTM neural networks, the introduction we wish we had. This video, together with a paper linked in the description, provides a general introduction to the inner workings of different types of neural networks. Note that the video is meant to give a brief overview of the paper. If you wish to implement a neural network, watching the video itself is insufficient. We assume a basic understanding of linear algebra. If you are unfamiliar with this subject, we have a couple videos linked in the description below that we highly suggest you watch. With all that aside, let's dive into what a neural network is.
In a nutshell, a neural network is a mathematical function that can approximate any function. This means that it can take in an input and produce an output that is related in some way. Imagine you are given the problem of classifying handwritten digits. It is easy for a human to do this, but it is incredibly difficult for computers to reach our level of accuracy. What if instead of explicitly coding in rules and features that, for instance, distinguishes a number 1 from 7, we train an algorithm to learn these features? This leads us to our first model, the multi-layer perceptron neural network. Training a neural network involves three main steps: feed-forward, backpropagation, and gradient descent. What you saw is called the feed-forward stage of a neural network, the first step to training a neural network. An input vector x is fed into the first layer of the network. This vector x is then squished by what is known as the activation function. This scales the input between a range we can work with. It is then multiplied by each one of these weights represented by the lines connecting the neurons. This operation is represented by taking the dot product of the input vector x and the weight matrix w. This will give us the values for our second layer of the network. The new vector is squished again and multiplied by our next weight vector. The result of the final operation yields the network's prediction of vector y for the input x.
But this prediction is likely wrong because our weight matrices were initialized at random. The green dot on the left is what our network predicted, and the red dot on the right is the actual value. To fix this, we compute how wrong our predictions were compared to the real y vector, and we simply need to minimize this error. Some very smart people came up with a process called backpropagation. We essentially compute the gradient of the error with respect to each weight to determine how to update the weights so that the error decreases. We then use gradient descent, or any optimization function of your choice, to minimize this error by shifting the weights in the negative direction of the gradient by an amount proportional to the gradient. After we do this a couple of times, our output gets closer to what we want. At a high level, this is how a neural network is trained.
But there is one big limitation to this model. It does not account for the order in which they see the training data. A model like this would struggle to perform tasks that involve time series data. This led to the creation of the recurrent neural network. A recurrent neural network contains a cell state vector that is passed in as an input to the next cell in the layer. This allows the RNN to remember things that happened in the previous time step. This allows us to do things like speech to text, predict stock prices, or classify EEG signals. However, RNNs also have a limitation. As you include more time steps into the model, we encounter the vanishing or exploding gradient problem. When we perform backpropagation in an RNN, we must calculate the gradient of the error with respect to the W matrix at every time step. We then add all of these gradients up and use that to update our W matrix. However, if the gradient of our cell state vector with respect to the weight is small, when we compute the gradient of error with respect to the weight, it will be very small. So small, in fact, that the network can no longer learn anything. This is because the error for a time step depends all on the previous time steps. As the number of time steps increases in a network, the faster the gradient vanishes.
How do we fix this? First, we should decide what information to keep and discard from the previous time steps rather than keeping everything from the previous cell state. To do this, we add a forget gate that decides what to discard from the previous cell state. We also need to decide what new information to add to the cell state. We do this using an input gate and a tanh layer that creates our candidate vectors. These two are multiplied together to determine what to add to the cell state. Finally, we need to determine what to output as our hypothesis, or our y vector. This is simply an output gate that decides what to let out. What we just built is called a long short-term memory neural network. It is capable of remembering long-term dependencies without encountering the vanishing gradient problem. For a long time, this was the state of the art for speech-to-text and translation. Now, let us talk about the implementation of the LSTM model. In this case, we're going to create a model that can predict text. To begin with, let's specify our model over here. We begin with the LSTM layer. Next, we add a dense layer. The job of the dense layer is to map numerical values of the vector representations of letters back to their letters. We need to use the dense layer so that the model can understand which numbers correspond to which letter, as it cannot read strings. Finally, we specify an optimizer to train our model. Once we have our model, we can begin to fit it to our data. Fitting is analogous to training. The model is fed a corpus of the text many times until it learns the patterns between the input and the output. In this case, the input is a vector of text, and the output is the same vector of text but shifted down by one time step. This way, when the model trains, it learns to predict what comes after each character. Looking at the first training example, we can see that what the model produces is pretty much gibberish. However, after many training examples, it begins to produce more coherent sentences. Given more time and resources, a model like this can create more accurate and more logical sentences.
All of these ideas are discussed in more detail in our paper. Please note that the filming of this video, there may be some errors in our paper as it was written for a school project. Please double check with other sources and let us know if you spot any problems. Thank you for watching.